Good afternoon. My name is Yoshinori. So I'm a production engineer at Facebook. So for those who don't know, so production engineer at Facebook means pretty similar meaning as a SRE. So I'm SRE at Facebook, and I'm also a creator of a database engine called MyRocks, which is I'm going to talk about today. So MyRocks is a MySQL database, and at Facebook, so we are a huge user of the MySQL database. And historically, we used MySQL InnoDB, which is a default transactional crash-safe database engine for our main users database. So users database stores almost all Facebook activities, like likes, or comments, or shares. So almost all Facebook activities are stored in a MySQL database, and which was backed by InnoDB database. But recently, we migrated from InnoDB to a new MySQL-based storage engine called MyRocks, which is more space-optimized database. So today, I'm going to talk about the migration stories from InnoDB to MyRocks, which were both MySQL database, but backend database implementation is very different. So I'm going to talk about today about Facebook MySQL database and the users database overviews, and what is MyRocks, and how we migrated from in production database, and what production issues we faced during migrations, and several lessons learned and summaries. So MySQL at Facebook. So we are a huge MySQL user of the MySQL database users. So we historically used MySQL 5.1, which was very old version. And about 4 years ago, we migrated from 5.1 to 5.6, which is relatively newer version, but not the latest ones. So 4 years ago, it was the latest, but after 4 years, so 5.6 is pretty old. But currently, it's based in MySQL 5.6. And Facebook has a dedicated MySQL engineering team, which creates many extensions on top of the Oracle's MySQL. So MySQL is now owned by Oracle. So I used to work at MySQL company, then was acquired by Sun, then acquired by Oracle. Then I left the Oracle, and now I'm at Facebook. But there are large MySQL engineering team at Oracle. They create features on top of official MySQL. But at Facebook, we also have not a big, but about 10 people working on the MySQL internals to add features to support our production workloads. So we have MySQL engineering team at Facebook, and we work very closely between SREs and MySQL software engineers. And we created many features on top of MySQL 5.6 to support our services. And we also working pretty closely with Oracle. So Facebook does not compete very much with Oracle. So our relationship with Oracle is pretty good. So we started working with Oracle to take our patches into official MySQL. And the latest MySQL version is MySQL 8.0. So we started porting our existing patches to MySQL 8, and we researched to deploy in production. Not ready yet, but we started seeking how hard it is to deploy the new version in our productions. The UDB, so this is the main topic, which is a users database. So users database is by far the largest database at Facebook, and it is also very critical. So it stores the social graphs. So users, Facebook people's activities like likes or comments or shares, whatever. So these activities are stored in MySQL database. So apparently, single MySQL database instance is not enough to handle our social workloads. So it's massively sharded. And our UDB is the main database. We have a huge record cache on top of MySQL database, which is called Tao. There is a paper about it, so it's not open source. But most read requests hitting the cache. So, but if cache misses, or when people writing comments, for example, these are the write requests to MySQL database. So some cache misreads and writes are coming to MySQL database. So if MySQL database is slow, then it directly affects the Facebook users' experiences. So the latency has to be low enough. So we pay enough care to make MySQL fast enough to support our workloads. At Facebook, we don't run MySQL or any other softwares in the cloud. So we cannot use the cloud providers features like Amazon Aurora or the Microsoft Azure SQL servers. So we have to operate by ourselves. So we automated almost all features like backups or provisioning or automated MySQL instance failovers or the recoveries or reimaging. So almost all operations are automated. And the last point is actually the most important topic for today. So we use Pure Flash, the flash storage on our main database. So a couple of years ago, we used hard disk drive. But as you know, the hard disk drive is pretty slow. So now the flash is modern, and which is much better for handling database workloads. So we have used flash for a long time, and now in our main database, we use 100% flash for storage. So like many other databases, internal or external MySQL or any other databases, so flash is very fast, but it's much more expensive than hard disk drive. So UDB is no exception. So in our database, the bottleneck is space. So it's pretty much constrained by space, and CPU and I/O are pretty idle. So not idle, but it's far from a busy rate. So we are constrained by space. So that's why our MySQL engineering team spent years to save space from our InnoDBs. So MySQL InnoDB has a feature called a compressed InnoDB compression. But unfortunately, due to architecture limitations, even with InnoDB compression, the space could not be saved enough. So there were a bunch of efforts at Facebook to save space in our UDBs. So one of the research projects was a couple of years ago, people tested HBase to run on the UDB. So that saved space, but we couldn't run on that. So that's why a few years ago, we started researching another database called RocksDB. So RocksDB is a fork from Google's the LabelDB, which is a key value store, the log structured merge the key value stores, so which is written in C++. So it's very modern, and it saved space a lot compared to a traditional B tree like InnoDB. So after researching RocksDBs, we tested and concluded that we could be able to run on our main database, the UDBs. So that's why we decided to integrate RocksDB and MySQL, and we finally created a MySQL database called MyRocks. So MyRocks is MySQL on top of RocksDB, so which is log structured merge tree database, so which is fully open sourced. So you can download from a public GitHub, now Microsoft. So, and it's distributed from major MySQL service providers like MariaDB or Percona. The main point of the MyRocks is, so MySQL has a pluggable storage engine architectures. So we used to use the InnoDB, which is transactional database, but the MySQL clients, like a Java or C or PHP clients, connect to MySQL database by MySQL protocol, then sending SQL statements. Then MySQL sends a query to InnoDB. But by adding a RocksDB as a storage engine, clients don't have to change anything. So just declare that this table is RocksDB, MyRocks. Then just sending the same queries, then MySQL automatically sends the queries to MyRocks database and handling the queries. So by doing this technique, so applications don't have to change anything, but just switching a table from InnoDB to MyRocks, then we can get full advantages of the LSM. So MyRocks' initial goal at Facebook was, as I said, so we use pure Flash, and Flash was we are constrained by space. So before migrating from InnoDB to MyRocks, so on our InnoDB servers, so it's mostly constrained by space. So CPU and I/O was pretty idle, like 20% or 15%. So it's far from a bottleneck. But the space was busy. It's pretty fully utilized, about 90%. It's constrained by space. So we could not add more data to this machine because the space was nearly full. So by switching to MyRocks during our experiments, so we could save space from InnoDB to MyRocks by 50%. So from 90% space to 45% space without increasing the CPU or I/O very much. So due to architecture differences, so RocksDB, like a LSM database, is saving space a lot. And the writes are pretty fast, but the reads are more expensive. But at Facebook, so we, like many other services, the web services have a huge cache. So most cache hit in the, most read requests hit in the cache. So the read queries are not many sent to the MySQL database. So that's why our CPU didn't increase much and I/O didn't increase much. That just space was saved by 50%. So by saving space, then we could add another MyRocks instance to the same machine. So by adding the second MyRocks instance in the same machine, so this means in the end, so we can save the number of machines by half by migrating from InnoDB to MyRocks. So this is a huge deal for us. So that's why we spent a couple of years to migrate from InnoDB to MyRocks. So the biggest objective of the MyRocks development was migrating from InnoDB to MyRocks. So we added features to match the InnoDB. For example, the InnoDB uses a special index format called a clustered index. So we added the same feature in MyRocks. And MyRocks has several extensions to make the read pretty efficient, the Bloomfield or column families. And we added support for transactions like and consistencies between the MySQL, the binary log, and the RocksDB, or the repeatable read or read committed. So these are the basic transaction capabilities. So RocksDB didn't have that before the MyRocks development, but we added that support because it is very important for critical databases. And migration involves the data loading. So we made data loading fast enough, so I will talk about this later. And since this is a new database engine, so many times people want to do some experiments, like trying new parameters or adding new parameters. So we made most parameters that can be changed online, so without restarting MySQL databases. So TTL is a feature that doesn't exist in InnoDB. So this is pretty common in the LSM database like HBase. So that's why we added that support. The TTL is a feature to purge the data older than a couple of days, for example. So normally, when operating database services, so if people want to drop all the data, then in MySQL, typically people create partitions, like partitions one older than 1 week, for example. Then when specific date passes, then people run the older table, drop partition to specify drop some older partitions. So with TTL, so these operations can be done automatically. So the DBS pains are a bit mitigated. So online backup, so online physical backup and logical backup. So at Facebook, so we use both. So at Facebook, we take logical backup. Logical means dumping by SQL statements, the logical. So logical backup for disaster recoveries. And we take a physical backup to create another replica instance in different regions. So these are pretty essential features, so we implemented both for MyRocks. So there are several trade-offs. So MyRocks has advantages over InnoDB and disadvantages over InnoDB. So major advantages of the MyRocks is much smaller space. It's half compared to a compressed InnoDB. So in many cases, people don't use a compressed InnoDB, so just uses a plain compact InnoDB format. Then you can compress, save space by about 75%. So it's just 4 times smaller just switching to MyRocks. And writes are faster because of the LSM architectures. And also the bytes written to Flash is also small. So this means you can use the same Flash devices longer period compared to InnoDB. So as you know, the Flash has a write lifetime. So if you write 100 megabytes per second, so all the time, then Flash will burn out. So you cannot use the Flash anymore. By writing less bytes to Flash, then you can use the Flash longer period, or you can use more affordable Flash that supports lower the write life cycles. So these are pretty big deal for when using Flash. MyRocks has disadvantages compared to InnoDB. So at Facebook, we targeted to migrate from a main user's database, but we have lots of the long tail, the many small services. But for many small services, it's not ready yet to migrate to MyRocks. So it lacks several features like foreign keys, full text index, special indexes. These are the common InnoDB features, but we don't support in MyRocks yet. And MySQL has a replication format called a statement-based and row-based. And in old MySQL, so statement-based was a common binary log, the transaction log format. But in MyRocks, we don't support that. So you have to use row-based binary log. And so this point is probably the most important part, but the reads are slower than InnoDB, especially if almost all data fit in memory. So almost all benchmarks shows that the MyRocks is slower than InnoDB. So this is an important limitation, and we are working to make it faster. But technically, the LSM database is write optimized. So the reads are slightly less efficient compared to read reads. But since the MyRocks most use cases targeted objective is saving space. So if database is very small, then it's not a big deal to save space. So we continue to recommend that they're using InnoDB for small databases. And there are many tuning options beyond buffer pool, like Linux kernel versions, file system, plume filter, compactions. So we are trying to define a more optimized formats. So these are the MyRocks overviews. So next week, I will talk about how we migrated from InnoDB to MyRocks in productions. So migration is just one word, but there are many technical challenges. So the most important part was the downtime. So creating MyRocks instance, so there are InnoDB instances and serving production traffics. So we wanted to migrate to MyRocks. But how to migrate without downtime is an important topic. And how to migrate within reasonable time. So we have many MySQL servers, but if it takes multiple years to migrate, then it's pretty painful, right? So we wanted to migrate fast enough, so especially loading data, which is one of the most painful parts in my databases. And after migration, so how to verify the data is correct? So MySQL database, the persistent services. So if data is corrupted, then fixing data is really hard. So to verify data is consistent, there are some techniques are needed. And the last part is serving write traffics. So MySQL has a role called primary and replica, or master and slaves. So like many other databases, so there is only one the masters that serves write requests. So if master is broken, and if there is a bug that writes are corrupted, then the database is corrupted. So this is a huge problem. So testing the serving write traffic is really important. And after migrations, then continuously monitor the resource usages, like I/O, the CPU, or memories, or query plans, like a query optimizer uses wrong index and suddenly takes lots of CPUs, and that's a huge problem. So query plan outliers, or stores, or crashes, so these need to be continuously monitored. So the first part was creating a MyRocks instance without downtime. So in MySQL world, this is relatively easy. So just, this is a pretty common replication environment at Facebook. So we have one masters and multiple slaves. It's a read replicas. So all write requests are coming to the masters, and the reads are served by a slave, the replica instances. So all of them are in InnoDB. So the migration step was the stopping from the slave, then dumping from an InnoDB database, then dumping as a SQL, the text, then loading into a MyRocks database. So creating an empty MyRocks table, then loading the SQL the data, text data to MyRocks database. After that, replicating from InnoDB. So MySQL replication is engine independent. So the MyRocks instance can be replicated from InnoDB, and so this technique was possible. The next part was data loading. So how to create a MyRocks instance fast enough was challenging. So this is a very rough picture about how write requests are served in the LSM database like MyRocks or RocksDB. When you commit transactions, then first the data is persisted in a transaction log called write-ahead log for crash recovery purposes. Then it's written to a memory called a mem table. Then after mem table gets filled, then first data file called level 0 SST file is created. And if there are many SST files in level 0 created, then another process called a compaction happens to create the more space-optimized files in under level, the level 1. Then this repeating these cycles, then finally the max, in the max levels, then data files are created again. So in many cases, there are about 5 or 6 levels in RocksDB. So this means even though you just write 1 byte, the 1 byte commits, the byte was written multiple times. So the write amplification is it's much larger than 1. It's like 5 or 6. It's pretty common. So even though the RocksDB is pretty write optimized database, it's still write amplification is pretty high. So during the data migrations, so we just dump from a primary key, dump by primary key, then loading into the RocksDB table. So we wanted to reduce write amplification to just once. So we added a special feature called data loading, the fast data loading features. So this is basically, if the data was sorted by primary keys, then it bypasses all of the write-ahead log and mem table or upper the level SST files, just creating the final the data files. By doing so, we could migrate huge hundreds of gigabytes of data just 1 hour or even less. So I created a first MyRocks instance, then second MyRocks instance, how to create second MyRocks instance without downtime. So this was relatively easy. So just we created an online backup tool called MyRocks Hot Backup, which is a binary copy tool from a running MyRocks instance to create another running MyRocks instance. So this is pretty similar to InnoDB's the extra backup, which is an online backup tool. So we created a very similar tool to just run the physical copies. So this does not need to stop the source replication slave. So this is much easier to run. So next part is testing the masters. So masters have write traffic, so which is really important. So we spend a lot of time to testing that. So we have a plugin called the auditing framework, auditing and shadow framework. So MySQL has a feature called audit plugins that captures all queries sent to a MySQL database. So we used that tool, and we extended a feature to capture queries, then sending the captured queries to test MySQL instances. So by sending the test queries to test instances, then we can verify that the data, new MySQL servers can handle read and write requests correctly. So we utilize to verify that MyRocks instances could be run on the masters. So like sending to the MyRocks master instances and verify that client errors are the pretty reasonable range. And we also reload queries that is not compatible with the MyRocks databases. So after verifying MyRocks works with the shadow systems, we promoted MyRocks as a master. So promoting MySQL instance as a master is just done by one command called a change master statement. So this was relatively easy, but as I said, so testing that was a really hard part. After MyRocks master working pretty well, then finally we replaced all InnoDB replica instances with MyRocks and discarded all InnoDB instances. So these are the full migrations what we did so far. But during the migration or after migrations, so we encountered several production issues. So from now, I'd like to share about the 4 different production case studies. So it's pretty technical, but it should be interesting. Some of them are pretty interesting. So before explaining about the case studies, so let's go back about the InnoDB and MyRocks differences from SRE point of view. So the probably most important part in MyRocks was that server is busier because we run more MySQL instances. So after switching to MyRocks, the space was half. Then we added another MyRocks instance to utilize machines. So this means the same machines have 2x read and write workloads. So the machines are busier. So busier machines often have more problems than idle machines. So it's pretty expected that high density the MyRocks machines to have more problems. And the RocksDB is much newer database. So InnoDB is a very mature database. It's really stable. But MyRocks is a newer database that changes rapidly. So changing rapidly means it has many modern features, but from SRE's point of view, it may have more bugs. So SREs can be busier by using more databases that change rapidly. And from database point of view, so MyRocks and RocksDB relies on buffered I/O, while InnoDB relies on the direct I/Os. So direct I/O and the buffered I/O are pretty different. And direct I/O depends less on Linux kernels, but using buffered I/O, like the RocksDB or HBase, so these databases rely on buffered I/O, and they're heavily dependent on the Linux kernels. And another difference is for large transactions, the commits need more work than InnoDB. So in MyRocks, all changes, uncommitted changes are kept in memory. And when transaction is committed, so everything is written to RocksDB's memtable at once. So this means when you're running a large transactions, then commit may take more time. And as I said before, so there are many tuning options beyond the buffer pool. So the tuning is a bit harder. And the last part is a good news that faster writes means MySQL replication lags less often. So when operating a MySQL database, it's a common pain point that the replica lags. So replication lags, then it's pretty pain point. But when operating MyRocks, then it lags much less often compared to InnoDB. Okay. The first issue was stalls on commit. So when testing a MyRocks master instances, so we observed that every few minutes, Then on busy machines, we started observing that the commit, just a commit, transaction commit, takes 100 milliseconds to a couple of seconds. So this was, we didn't observe that in InnoDB. So this was pretty annoying for us. So we started investigations. So first, we needed to collect data. So there are several indicators in MySQL to know if the servers are storing or not. Like a show global status shows that occasionally higher number of threads running, so running database transactions. So if it's constantly exceeded 100, so this is pretty unusually high. So this is indicating the servers are storing. And show process list is a command to print all of the MySQL client activities. So, and by combining these, so we could find that many MySQL clients are waiting for the commit statements. But CPU or I/O and flash devices were not so much busy. So we started digging into several logs. So this is a command log atop, which is captures the top output every few seconds. Then the system and the users, so these are the shows we have this machine about 56 cores, but only 7 cores were used for system and 21 was used for users. So not much idle. But there were quite a lot of page scans and page steals and page scan stores happening. So it's kind of the page cache stores were happening in this database when commit stores happened. So this was pretty much suggesting that we have an issue on the buffered IOs. So on buffered IOs, so RocksDB has currently very limited support for direct IO, so that's why we are using buffered IOs. But commit path involves lots of memory operations, like a mem table writes, or writing to binary log or write-ahead log, which are transactional logs, which cause the kernel memory allocation stores. So this was a problem for us. So to mitigate these stores, so we upgraded our Linux kernel from 4.0, which was relatively old kernel, to a relatively newer kernel, 4.6. So kernel 4.6 fixed lots of problems about that. So after fixing that, changing that, so we observed much fewer the commit stores. And we also changed data loading queries, like schema changes, to fully utilize the bulk loading that bypasses all mem table or write-ahead logs. After these changes, so these commit stores almost dropped to nearly 0. So transitioning to direct IO, so we have not done yet, but we are planning to switch from buffered IO to direct IO in MyRocks and RocksDBs. So several benchmarks, both internal and external benchmarks, showed a bit better scores with direct IOs than buffered IO, even with the newer Linux kernels. But there are several challenges in addition to fixing just supporting a RocksDB for supporting direct IO. So the biggest limitation is that Linux does the inefficient or the undefined behaviors when mixing the buffers and IO and direct IOs. For example, if there are dirty pages in the page cache with buffered IO, then all these with direct IO are serialized until dirty pages in page cache disappears. And there are several limitations. So normally, we shouldn't mix direct IO and the buffered IO. So not just MySQL database servers, but also other supporting tools like backups have to use either all direct IO or all buffered IO. So we are in the process of just using either of the two. So we are fixing not just MySQL database, but also the supporting tools to use direct IO. The second case was pretty scary bug, but we deleted several records, but on the secondary indexes, the records reappeared somehow. So this turned out to be a RocksDB bug that on some rare cases on heavy deletions, tombstones means delete markers in RocksDB might not have been handled correctly. So some kind of data corruptions. So how did we find this bug? Then we ran the continuously, we did consistency check, comparing accounts, so checksums between primary key and secondary keys. Then we found this bug. So after finding this bug, the finding the root cause was the next step. So how did we find the root cause? Then we drained the affected MySQL instance for investigations and found out the timestamp, the record, when the record was changed for that had the extra records, and searched the data files that contained the keys, and looked into RocksDB logs and checked how these data files were created. So RocksDB logs contains that information about how the data files were created. And we worked with Facebook's RocksDB engineering team to figure out the possible causes and relevant diffs. So finally, we found that a new feature called a level 0 to level 0 compactions caused bug. But probably the most important part was the finding such issues. So how many people ran the consistency check between primary key and secondary keys? So, oh really? This is pretty good practice, but actually this may happen with any engines. So MyRocks is a new database, so we hit this bug, but actually we hit this bug in InnoDB a long time ago. So this is relatively good practice to check consistencies. So the easiest one is just counting check between primary key and secondary keys, like select count from T, force index primary key, the union, then select count from T, the same table, force index the secondary keys. So these run the same transaction snapshot, then getting the counts from the same table with different indexes. If the record count is different between indexes, then this is a sign that data is corrupted, right? Because it's the same table and different indexes, so they should be consistent. So not just count, but you can check the records, the column consistencies as well. So it's a bit complex SQL functions, but you can check consistency as well. And checksums across instances. So this primary key and secondary key comparison was just from a single instance. But in MySQL, there is a technique to compare consistencies between the one master or slave and the other master or slave. So comparing different instances is still possible. So MySQL has a feature called global transaction ID, which is a global transaction identifier that was shared between master and slaves. By utilizing that, you can check the consistency between different instances. So we do that as well. But in many cases, just a simple the primary key and secondary key check could find most problems for us. The third case was another technically a bit complicated issue, was the counting from empty MyRocks table that suddenly started taking a couple of minutes. This was scared us a lot because the empty table should take just sub-seconds, right? Or even the microseconds to return the table was empty. But suddenly it takes a couple of minutes. So we started investigation why this is happening. So first step was reproducing. So when such problems happened? So we narrowed down by sending several statements. It didn't reproduce with insert, and it did not reproduce with selecting records with primary key lookups. And sometimes they reproduced on range scans, so range scan by the sum of secondary keys or order bys. And sorting order actually mattered. So order by ascending, it didn't happen, but order by descending, it happened. And Bloom filter also mattered. So there are a bunch of patterns tested, and we concluded that on several patterns, then the problem happened. So after verifying the reproducing this case, the next step was finding the root cause. So we debugged with the reproducible test cases. Then we concluded that there were 4 different bugs in both MyRocks and RocksDBs. So it's a bit complicated, but the steps, probably this was the most difficult bug we found when operating a MyRocks database instance. But the first bug was when we delete records, then RocksDB issuing got tombstones, which is a delete markers in RocksDB. When delete markers, when compaction happens, then delete markers go to the bottom levels. But after reaching the bottommost levels, then delete marker is expected to be deleted because it is not needed anymore. But this didn't happen when running transactions like consistent backups. So the many delete markers remained in many data files. Then this called some range scans seeked these tombstones, even though they are completely different data areas. So fundamentally, so these are multiple bugs associated, so involved in this bug. So, and hopefully we could fix these problems after finding the root cause. The last part was a bit funny. It's a little bit easy bug, but it's happened in production. So writing core file crashed machines. So after enabling core files for MySQL reprocess for debugging easier for MyRocks, then we started observing more host reboots than unplanned kernel crashes than before. So after seeing that, we investigated the logs. So MySQL error logs showed that it tried to write core files before kernel crash. But core files were not actually written. And we, as I said before, so we archived the logs, the top histories we called ATOP. So ATOP shows that the virtual memory in MySQL process was extremely large. So virtual memory didn't matter much. So we used MyRocks with a memory allocator called JMalloc. So JMalloc uses a relatively large, sometimes terabytes of the virtual memory. But residential memory was a couple of gigabytes. So the virtual memory is normally OK when operating database services. But when writing a core file, it matters because the core file is created based on the virtual memory. And our default core file dump location was a root partition, and which was ext4 file system. So when we started enabling core file when running a MyRocks, then when the MySQL crashes, they try to write a core file to ext4 partitions based on the virtual memory, which can be hundreds of gigabytes, but which is larger than our root partitions. So we couldn't write the file, create a file. So growing RSS is fine. Growing RSS is a sign of memory leak, but but if RSS is stable, then that's OK. But the large virtual memory is a problem when writing a core file. So that's why actually the Linux didn't handle pretty well. So instead of just rejecting, then it's stored a long minutes, then finally it reboots the machines. So which is pretty annoying on the MySQL databases. So we are almost forced to disable the core file, so because we cannot accept such host crashes. And trying to print stack traces by pstack before aborting MySQL. So in many cases, what we wanted was stack traces when MySQL is crashed. So core file is pretty nice to have, but even with just stack traces, we can find many issues. And we are also working in progress to just compress core files prior to dump. So we just writing only, so core file is very sparse files. In many cases, after compress, then the core files can be hundreds of megabytes. Then we can write to a local disk. Yeah, so these are the 4 different production issues. So we learned a lot during the migrations and deployment. So we learned lots of lessons. But these are the two probably the most important lessons for me, and probably this is pretty useful for you as well. So first one was learn how core components work. RocksDB depends on Linux more than the InnoDB. So understanding how Linux works helps to fix issues faster. In many cases, people, the SREs or software engineers use cloud services as a black box. But understanding how they work, that often helps to fix problems earlier. And do not ignore outliers. So in many cases, we monitor average of P99s. But in our cases, so many of our issues happened on only 1 or 2 instances. So when we checked just P99, we missed these machines. So normally, average of P99 is a good indicators, but just don't ignore outliers. So if some weird issues happening on 1 or 2 machines, then don't ignore them, just investigate them and see what is going on. Yeah. So our current version status was, so hopefully after fixing these issues, then we completed the InnoDB to MyRocks migration in UDB, our main database. And we saved about 50% space in UDB compared to a compressed InnoDB. And we started migrating on, working on migrating other large database tiers from InnoDB or other databases to MyRocks. So hopefully we may be able to announce some of the other migration stories in the coming weeks or months. So these are our migration stories. So thank you for listening.